So recall that we've defined our set of natural numbers to be the smallest inductive set, and we gave an ordering on the set of natural numbers where we defined m to be less than n if and only if m as a set was contained in the set n. And in today's video, our goal is to show that this is a linear or total ordering. So first off, recall that an ordering is said to be strict if it is asymmetric, which means that there does not exist a pair of elements, well, in this case, particularly in the natural numbers, such that both x is less than y and y is less than x at the same time. And the second property it must satisfy is that this is transitive, which means that for any triple x, y, and z belonging to the natural numbers, if it's the case that x is less than y and y is less than z, then it must be the case that x is less than z. We then say that an ordering is comparable, or we say that all elements are comparable if for any pair of x and y in the natural numbers, it's either the case that x is less than y, y is less than x, or that they're equal. So they can always be either they're the same element or they do compare to each other in this ordering. It's defined on all pairs of natural numbers. So the goal in today's video is to prove that both of these statements hold, and that is what the definition of a total or linear ordering is. So we're going to make heavy use of the lemma that we proved in the last video, and that is the lemma which said, well, it had part 1 was that 0 is less than or equal to n for all natural numbers. And the second part of that lemma, which we're going to use a lot, is that if k is less than n plus 1, then this implies that k is less than n, or k is equal to n. And this holds, of course, for all k and n in the natural numbers. So the first thing we're going to prove to establish these goals is the transitivity. So we're going to consider some k less than m, some m less than n, and our goal is to show then that k is less than n, and this should work for arbitrary natural numbers. Well, what we're going to do is actually set this up by induction. So I'm going to take my statement to be the statement that for all k and m in the natural numbers, k less than m, m less than x implies that k is less than x. So if we check our base case, plugging in 0 to this statement, well, this would be the statement that k is less than m and m is less than 0, implying that k is less than 0. But we already know from the previous lemma that n is greater than or equal to 0 for all natural numbers. So this is false. And whenever we have an implication of statements, say P implies Q, if the antecedent, the hypothesis, is false, then the whole statement is vacuously true. So we have false implying false. So overall, the statement P of 0 is true. So now to apply induction, we're going to assume that the statement holds for some n. That is, we're going to assume that k is less than m, and m less than n implies that k is less than n. And what we want to do is show that the statement holds for p of n. So we have to take, for our hypothesis, we're going to suppose now it's the case that k is less than m, and m is less than n plus 1. And our goal is to show now that k is less than n plus 1. Well, we know from the part 2 of the previous lemma, there's only two possibilities when m is less than n plus 1. Either it's the case that m is less than n, or it's the case that m is equal to n. So what happens when m is less than n? Well, now we can apply the induction hypothesis, right? So we have k less than m, we have m less than n, and by our inductive statement, we can conclude that k is less than n, and we know that n is less than n plus 1. And this is exactly what we wanted to show, is that k is less than n plus 1. Now, on the other hand, the other possibility is that m is equal to n, well, in which case, our hypothesis is that k is less than m. So that means, simply replacing the m with n, that means that k is less than n, which again is less than n plus 1, which is exactly what we wanted to show. So therefore, we know that the statement p of n plus 1 holds, and thus, by the principle of mathematical induction, we've established transitivity for this ordering. The next thing to do is establish transitivity, which states that for any pair of integers, it can't be the case that both k is less than n and n is less than k. Well, notice by the transitivity property we just established, if n is less than k and k is less than n, we're now able to conclude that n is less than n. And so what we're going to do is actually prove that this is impossible, once again by using induction. So now our statement p of x is going to be the statement that x less than x is false. So our base case, plugging in 0 at p, well, this would be the statement that 0 is less than 0. And remembering our definition of the natural numbers, this says that the empty set is contained in the empty set, and clearly this is impossible. So we're going to assume that the statement holds for some piece of n where n is greater than or equal to 0. And, well, what this says precisely is that n less than n is false. So assume to the contrary that it were the case that n is strictly less than n plus 1. Well, there's two possibilities here again by the previous lemma. It could be the case that n plus 1 is strictly less than n, or the other possibility is that n plus 1 is equal to n. Well, if n plus 1 is strictly less than n, then since we know that n is less than n plus 1, we can combine these, again using the transitive property, to conclude that n is less than n, but by our induction hypothesis, we know this to be false. Okay, so the statement's false in this case, and if n plus 1 were equal to n, well then, once again, we know that n is less than n plus 1, so this statement becomes that n is less than n once we substitute the n in here. And, well, yet again, using our induction hypothesis, we know that this is false. So ultimately, we know that in any case, n plus 1 is less than n plus 1 is false, and therefore the statement that this is false, p n plus 1, is true. So again, we've made use of the induction hypothesis, and we were able to show that this is a asymmetric ordering. So now that we've established transitivity and asymmetry of the ordering, we know that we have a strict order on the natural numbers, and what remains to be shown is that the ordering is comparable. So that means that for any pair of elements, one is less than the other, or they're equal. So we're going to prove this by induction yet again. And this time we're going to take our induction statement to be that for all m in n, it's the case that m is less than x is less than m, or m is equal to x. So the statement, the base case statement, would be that either m is less than 0, or 0 is less than m, or possibly that m is equal to 0. So we know that m can't be less than 0 by the lemma we established in the previous video. And then the remaining two possibilities get packaged up into simply the statement that m is greater than or equal to 0. And by that exact same lemma, we know that this is true. So the base case does in fact hold. So we're going to suppose that it's true for p sub n, and we want to prove that the statement p of n plus 1 holds. So what it is that we want to show is that either m is less than n plus 1 is less than m, or m is equal to n plus 1. So there's a few possibilities. It could be the case that m is already less than n, and if that were the case, then since n is less than n plus 1, we would be done. That's one of the possibilities. The other case is that m could be equal to n, and in which case this is again less than n plus 1, and so we're done yet again. So the only other possibility to consider is that m is in fact greater than n. And so assuming that this is the case, what we're going to do is show that n plus 1 is less than or equal to m. If we can do this, then in either case, either we have n plus 1 is less than m, or we will have that m is equal to n plus 1, and this will finally establish the statement p n plus 1. So we're actually going to do an induction inception in this case, and we're going to prove another inductive statement within this inductive argument. And that is going to be the statement that n is less than y implies that n plus 1 is less than or equal to y for all n in n. So again, we look at our base case first, the statement when q is at 0. And this is the statement that n less than 0 implies that n plus 1 is less than or equal to 0. And again, our antecedent here, our hypothesis, is false by the lemma we previously established. So automatically the entire implication is true. So q at 0 holds. So we're going to suppose then that q at y holds for some arbitrary y. And we want to show that this implication holds for y plus 1. So we're also going to assume it's the case that n is less than y plus 1. And our goal will be to show that n plus 1 is less than or equal to y plus 1. So again, by applying the lemma from the previous video, there's really two cases that can occur if n is strictly less than y plus 1. Either it's the case that n is less than y, or it's the case that n is equal to y. Well, if n is less than y, then by applying the induction hypothesis, that is the statement for qy, that implies that n plus 1 is less than or equal to y. And since y is less than y plus 1, well, it's less than or equal to y plus 1, and thus we've shown that n plus 1 is less than or equal to y plus 1, which is exactly what we want to prove that the statement q at y plus 1 is true. Okay, the other possibility is that n is equal to y, but this means that n plus 1 is equal to y plus 1, and so again we get that n plus 1 is less than or equal to y plus 1. Okay, and so we've now shown by induction for this statement q that if n is less than y, then n plus 1 is less than or equal to y. So if we scroll back up, what we needed, this was the final part in our induction proof on the statement Pn that says basically every element is comparable with n. This was the only remaining possibility left to show, and thus altogether now we've finished proving the induction statement for P at n, and that means that we've now proved by induction that this ordering is comparable. Or rather, that every pair of elements is comparable in this ordering. And so we've shown now that the ordering on the natural numbers is comparable, it's asymmetric and transitive, meaning it's a strict order, and thus we've shown that the ordering we've defined on the natural numbers is a total or linear ordering. In the next video, we're going to come across a stronger form of induction. We're going to hash out a few more aspects of this order. And then after that, we're going to move on to a new section where we will prove facts about recursion on the natural numbers. And that's going to allow us to define things like addition and multiplication.